Restart the camera. That means we're in our last 25 minutes. Ah! Z1 equals x1 plus y1 plus y0 minus z2 minus z0. Now, if we have, yeah, we still have time to just multiply this out. So let's just make sure that this is correct. It's x1 y1 plus x1 y0 plus x0 y1 plus x0 y0 minus, remember, z2 is x1 y1 minus z0, which is x0 y0. So you take the x1, so this cancels, and x0 y0, this cancels. So you get x1 y0 plus x0 y1, which is exactly what you want for z1. So this is true. This is a correct observation. And notice that he's getting this with only one multiplication instead of two. Okay? So that means if he computes z2 and then with one multiplication, and then z0 with one multiplication, and then he computes z1 with one multiplication and then two subtractions and two additions. But additions and subtractions are easy. Those are linear time. Then he's using only 3 multiplications of roughly n over 2-digit numbers. Now, actually, okay, when you do these additions, then it can be like n plus 1, n over 2 plus 1. But, okay. So, is this fast? So in the lecture notes, I've actually done that for these things. I've actually worked out Z2 and Z0, and then I worked out this, and then plugged it all in, and it works. Okay, you do actually get this the product of these two numbers. I'm going to skip it because it takes a while. Does anybody really need to see that? No. Good. So how long does this take? Well, okay, so we saved one multiplication, but that doesn't really help us if it's just that multiplication, right? Because then, you know, we've saved like this, but we've got 3 times, instead of 4 times n over 2, we've got 3 times n over 2 squared. Well, that's only a constant factor, so we're saving like a quarter of the time. That's not going to help us. Of course, the trick is to use this recursively. So if you use this to compute to figure out your the product of your 2 n-digit numbers, by working out products of n over 2-digit numbers, and you work out those 3 multiplications of n over 2-digit numbers, and you work out those 3 multiplications of n over 2-digit numbers by each of those by 3 multiplications of n over 4-digit numbers. Okay, so how long does this take you if you do this recursively? Well, you get this recurrence, which is Tn equals 3 times the time it takes you to multiply n over 2-digit numbers, plus then something which is linear in n for the additions and subtractions. Yes, recursion, yay! Yes. So I think in the course notes, I think I said c was equal to 5. We don't really care what c is. We also don't care about this example, which is in the lecture notes. Yeah. 20 minutes. Okay, so if you get this recurrence, okay, so have you seen recurrences in discrete or something? Discrete 2? Yes, good. No, no. Ooh. Okay, I think that discrete 2 is not mandatory. Yes, no, okay, about half the people. Okay, if you have this recurrence that says this function t is the time it takes you, is some function of n, and it tells you how long it takes you. Oh, right, we didn't talk about worst case. Where is worst case? Worst case used to be up there. Right, usually if we're talking about complexity, yeah, I should mention this. Usually when we're talking about complexity, I mentioned best case. People don't usually care about best case. Usually what we mean is if we say the complexity of this is n squared, it means that for sufficiently large inputs, right, where n is the size of the paper you're giving me, or n is the size of the input, however you're measuring it. N could be the number of vertices in the graph, something like that, right? N is this thing that you want to measure in terms of, and you say, this takes n squared time. It means that as n goes to infinity, for some constant times n squared, plus something. So for sufficiently large n, it takes me about n squared time to solve any instance of size n. Right, so this is worst case. Now, you can also talk about average case. It'd be like, okay, over all the instances of, if for a sufficiently large n, over all the instances, on average, it takes me n squared time. Okay, if you choose one, well, yeah. Okay. You can talk about the expected case complexity. Yeah, okay. So usually we talk about worst case. It is usually talk generator functions. Ah, yeah. Oh, yeah, I remember generator functions. Don't worry, we're not going to do generator functions in this class. We're going to have to do recurrences because Val makes me. Okay, so let's get going. So this is some function. So we're going to say, let's say that t of 1 equals 1. Right? So we need some base case. So there are lots of books about generator functions and recurrences, and we have enough to cover in this course without going too deep into this. Okay. So how are we gonna figure this out? Well, what you're gonna do is you're gonna say t of n, take this, just assume that t of 1 equals 1. But I want it to be written up here. So this equals 3. Well, we can plug this in and say, okay, well, what's t of n over 2? That's 3tn over 4 plus cn over 2 plus cn. What's that? Well, that's just, what is tn over 4? Well, that's tn over 8 plus cn over 4 plus cn over 2 plus cn. Okay. So if we say, okay, we expand it out I times, what are we going to get? We're going to get 3 to the I times t of n over 2 to the I, and then plus sum of j equals 0 to I minus 1. Well, we're going to get, okay, cn, sum j equals 0 to I minus 1, I think, of, now remember, this isn't being multiplied by, this isn't being multiplied by any 3's. This is being multiplied by this 3. This is being multiplied by this 3 and this 3. Okay? So it's actually going to be 3 over 2 to the j. Okay? So, and then you play around with this and you think, okay, so you plug in I equals log n, right? So let's plug in I equals log n. So can you still see this down here? For I equals log n, this is going to be, I need this space. equals log n. This is 3 to the log n t n over 2 to the log n plus cn sum j equals 0 to log n minus 1 of 3 over 2j. 3 to the log n, this is 2 to the log n is n, so this is t of 1, this is 1, so this is just 3 to the log n. And then this thing is, I worked this out last night. This is at most log n times, yeah, okay. So you have cn. So let's just, this sum is bounded by log n times 3 to the log n over 2 to the log n. Oop. Just a second. It's hard to do this. Yeah. Oh, okay, I worked this out and then I just skipped over it. Okay, so this works out to be order 3 to the log n2. Okay. So this is all just order 3 to the log n. If I have more time, I can do this. So what is this? Well, 3 to the log n equals 2 to the log 3. LG means log base 2, okay? It's very frequent in computer science. We need log base 2 all the time. Times log n, and then we can just swap these around. So this equals, I'm just showing, this is easy, but it's just a neat trick, and people got stuck on it in a previous year. Log n log 3 equals n to the log 3. So this is order n to the 1.58 something, something, something. Okay? So it's better than n squared. Well, 15 minutes to teach Strassen's algorithm. That's insane. Okay, so Karatsuba's algorithm, you can do it in n to the, he showed that you can do this multiplication about n to the 1.58, n to the log 3. Okay? So this is, all right, so after thousands of years, in 1962, somebody figured out how to do multiplication in subquadratic time. Now, shortly after, people improved this. And actually, this is cool for people in Canada because this was studied. There was an algorithm called TOOM where instead of chopping stuff in 2, you chop it in k pieces and then do sneaky multiplications of n over k things, n over k digit numbers. And that was done by TOOM in '63, and that was reanalyzed by Cook in his PhD thesis at Harvard on the complexity of multiplication in 1966. Cook is Stephen Cook. He was my logic professor at University of Toronto. He'll come up again in the course because he's the P versus NP guy. Yeah, so it's cool so the other thing, there's probably a bunch of stuff, it's in the course notes, but another cool thing is that people actually figured out how to get this down to n log n, and they did that in March 2019. So about 6 months before the first time I taught this course at Dal, it was then, multiplication became n log n time. Okay, so that's cool. So addition is linear, multiplication is not worse than n log n. Okay, so now we can do We've done addition and arithmetic operations on numbers. So what else can we work with? Well, how about matrices? Number integers are a ring. Matrices are also a ring. We don't have time to talk about rings. You may have seen rings, fields, stuff. Okay, so you have addition and multiplication. So how long does it take you to add? Let's suppose that you can do addition of the components. How long does it take you to add an n by n matrix and an n by n matrix, assuming that you can add the entries in constant time? Well, right, you just add corresponding entries, right? So if you have A plus B equals C, then Cij equals Aij plus Bij. How many things do you have to do this for? Well, n squared, right? So matrix addition is O(n) squared time, assuming the elements can be added in constant time. Okay, what about matrix multiplication? So this gets a bit scary, because if you think about the algorithm we learned in high school, where it's A11, A12, A21, A22 times B11, B12, B21, B22, C11, C12, C21, C22. Okay, so to get an entry Cij, this is the dot product of the ith row of A and the jth row of jth column of B. So each of these are n entry vectors. So to do the dot product, okay, it's actually the transpose of the jth column of B. To do the dot product, you're going to multiply the first component by the first component, the second component by the second component, and then you're going to add all of these products up. That's going to take you n time, right? So to compute each entry of C, it's n time using the standard algorithm. And there are n squared entries of C if it's an n by n matrix. Right? So this is cubic. Now in numerical algorithms, you can, you have a matrix and it's like 1,000 by 1,000. Well, cubic in 1,000 is a billion. That's pretty nasty, right? Doing a billion, and then something. So if you're training neural networks or something like that, you can have to evaluate the product of polynomials if you're doing PageRank, something like that. Multiplying matrices is not easy, right? So let's see if we can do it in something. So the standard algorithm is cubic time. Standard algorithm is cubic time. So we'd like something better than that, subcubic for matrix multiplication. Now we actually don't know how fast you can multiply matrices. And it's an important question because multiplying matrices isn't just an important thing by itself, but it's used as a subroutine in a lot of other algorithms, including some algorithms we're going to see towards the end of the course for like counting paths and shortest path computation. And I have 8 minutes. So Strassen. So remember, this was after Karatsuba showed that you could do this sneaky divide and conquer to multiply integers faster. So Strassen did sort of the same thing, but for matrices. Now, I wrote out in the course notes. Okay, so here you have the standard. So what you would normally write is, like I wrote, Cij. So here C11 equals A11 times B11 plus A12 times B21. C12 is A11 times B12 plus A12 times B22, right? Right? You do, to get C11, you do this times this and this times this. To get C12, you do this times this and this times this. Okay, so if you actually write this out, C22 equals A12 B21 times B12 plus A22 times B22. Right, so how many multiplications are we doing here? So each of these we can think of, if we have n by n matrices, where n is some nice power of 2, for example, to keep things simple, and we've chopped it up into 4 submatrices. Each matrix into 4 submatrices. So this requires 4 submatrices of size n over 2 by n over 2. So how many multiplications of n over 2 by n over 2 matrices do we use? Well, if we just do this, we use 8, right? 2 for each submatrix in C. Are people still here? Yes, generally? Okay. So, if you do it the normal way, you use 8. Now that's 8 times n over, this is the same as with Karatsuba, times n over 2 cubed equals n cubed. We're not saving anything. But now Strassen realized, so he came up with 7, I believe 7. So he did the same thing for matrices, 7. Which I am not going to write out because that would take more than 5 minutes, but it's in the course notes. I also got it off Wikipedia. Because, hello. Okay, so as you saw, I've more or less memorized, like, I forget it, but every year you can memorize Karatsuba's the definition of Z1, Z2, and Z0, Z1, and Z2. The only tricky one is Z1, and that is just x1 plus x0 times y1 plus y0 minus Z2 minus Z0. Right? That's easy. Nobody, certainly not me, I have never memorized the Strassen's 7 intermediate matrices. So these are M1 through M7, and they are like the Karatsuba Zs, or Zs, whatever, but not easy to remember, okay? So what he does is for each of these intermediate matrices, you do some additions and subtractions and one multiplication, okay? So remember, additions and subtractions, they're n squared time, so they're easy. And then you've got 7 multiplications. So Strassen showed how to use 7 multiplications of n over 2 by n over 2 matrices, submatrices. Okay, so again, if we just do that once, it doesn't save us, but what's the recurrence? Tn equals 7 Tn over 2 plus Cn. We expand this out. I sent this to my mother for proofreading, and she tells me I'm not allowed to say expand out because it's redundant. Expand is always out. So that's why it just says expand in the course notes. Okay. So this is, I'm just gonna, if this is not recording, I'm gonna cry. No, it is recording. Okay, this, what you get is n to the log base log 7 order, n to the log 7. Log 7. And log 7, log 8 is 3. Log 7 is slightly less than 3. I think it's 2.807 or something. Okay? So, n to the 2.807 maybe. Okay, so, woo! Matrix multiplication in subcubic time. Now this, there was that, and then there were a chain of things where people were like pulling this exponent down. For a while, people thought it was going to be 2.5, but then it was pulled under 2.5. Then for a long time, the best was this algorithm by, I think, by 2 guys called Coppersmith and Winograd. And then a few, like 5 years ago, Andrew Strother, in his PhD thesis, he managed to get it slightly better. And then Vasilevsky-Williams got it slightly better. And then Legal got it slightly better. And now it's something like 2.37. And now every time it changes by this tiny little amount, the whole theory community goes nuts. And it's changing by things like 1 in 1,000. There was also a nice result recently. I'm over time. There was a nice result recently. People at MIT, somebody in Vampala, showed that actually you can do Gaussian elimination or something in slightly better than matrix multiplication time as it stands now. So they managed to find this way to get around matrix multiplication for something people thought you needed matrix multiplication for. So this is like theoretical computer science. It's like the gravitational constant. Like, do normal people really care what it is in its 5th decimal place? No, but physicists get excited about that. So, you know, I don't get super excited when this number changes, but some people do. So that was Strassen. In the next class, we're going to be doing the fast Fourier transform, which is showing, we saw integers are a ring that has addition and multiplication. Matrices are a ring that have addition and multiplication. Another ring is polynomials. Okay. So how fast can we, well, you can add polynomials pretty easily, right? That's, you just add the corresponding coefficients, but how fast can you multiply polynomials? And so to do that quickly, you use something called the fast Fourier transform. I'm not going to be teaching that though, because a friend who's a postdoc, he needs teaching experience, and also I never actually learned the fast Fourier transform when I was an undergrad. Because it's not something, if somebody said they learned it at that in Dirk Arnold's course, but usually it's not taught to CS people. But this guy, he's an electrical engineer, so he wants to